Welcome back. This is Thermodynamics 1 homework number 4, which is first law analysis on closed systems. Problem number 4 is one that I've defined. So we have a piston cylinder containing sulfur hexafluoride. Homework 4 is on closed systems, so typical piston cylinders. So we have sulfur hexafluoride that behaves according to the virial equations. So P equals RT over V plus B over V squared plus C over B cubed plus dot dot dot, but I only have up to the third virial coefficient. Okay. We have a 24 watt heat resistor. Okay, so 24 watts. Okay. It's turned on for 5 minutes. Okay. Time equals 5 minutes. Over the course of that 5 minutes, 3.7 kilojoules of energy is lost through heat transfer. Okay, so I also have another Q term here. That is, so this is a dot, this is an absolute, equals, what was it? 3.7. Okay, so 3.7 kilojoules. Okay. The initial pressure for this constant pressure process is 300 kPa. Okay, so P is equal to 300 kPa, which is equal to P1, which is equal to P2. Okay. What was the final temperature if the initial is 350 K? Okay. So T1 is equal to 350 K. So I could figure out the molar volume from that. I don't think I need to, but I could if I needed to. Okay. Because I could solve this as a cubic equation and figure it out. Okay, but I'm not going to. Okay, let's just assume things. Okay, let's draw our boundary. Okay, so we're going to assume that, okay, well, I think we need to, sulfur hexafluoride, so it's not an ideal gas. The heat capacity might not be constant, so let's not assume it's constant. We are going to assume that there's no shaft work. Okay. We're also going to assume that it's not adiabatic because I got heat coming in from two different. I got heat coming in and I got heat coming out. So this really should be a minus 3.7. It's closed. Okay, and I don't have any kinetic energy changes or potential energy changes. But other than that, I don't think I can assume much. Okay, so I have my system, I have my boundary, I have my assumptions. Let's start applying those assumptions to a mass balance. So let's see here. N dot I n minus summation of N dot E exit equals dN dt, control volume. Okay, that's 0, dN dt of the control volume equals 0, so dN equals 0, N2 minus N1 equals 0, N2 equals N1. Okay. Now the energy balance. Summation of n's n dot I h I plus 1/2 v squiggly squared I plus g z I minus the exits n dot E h E plus 1/2 v squiggly squared E plus g z E plus q dot plus work dot equals du dt plus ek plus ep. That goes to 0, that goes to 0. That doesn't go to 0, that doesn't go to 0, that goes to 0 because there's nothing coming in, nothing coming out. And so when I'm all said and done, I have Q, we'll call this QL and we'll call this QH. So we have QH plus QL, okay, plus work okay, equals du dt, my control volume. Kind of cleaning that up a little bit. Okay, I've got my total Q, I got my QH times time plus QL total minus PdV, V1 to V2, equals, MDU. Okay, so I've got that. So again, this is constant pressure, and so I've got Q dot H times time plus QL minus P, and this becomes V2 minus V1. Okay, those are totals, and this equals, so if I want to, I can put this as an M, or N, this is an N P V2 minus V1 molar, okay, and then I would have N U2 minus U1, okay. All right, so I know this guy, I know this guy, I know this guy, I know my pressure. I don't know if, yeah, it doesn't look like I know my initial moles. And I don't know I do know my initial pressure, and I don't know my initial molar volume. Yeah, well, I do know my initial molar volume because I know how much, I know the T and I know the P and I know B and C, so I can solve for V squared and V cubed. So I do have enough for that to get my V1 and my V2, because at least my my V1 and my V2. Well, my V1, maybe not my V2 yet. U1 minus U2 minus U1. Okay, well, I'd have to do a departure function for the sake of this problem. I'm not going to do a departure function. We've done departure functions enough, but I would do a departure function there. Again, I probably would need some T's and V's, or at least, I have P's, so I'd have to use those P's to solve for my V's, and I'd have enough, and again, I'd have my V's, and I have to kind of solve for my V's with respect to T's, or rather, solve for T, so T is really, P minus, I'd have to solve my V in terms of T, or vice versa, and then, I'd have some big complicated equation, and I'd solve these, etc. or something. Okay. But again, the whole point of these practice problems, these self-assessed problems, is really to get kind of down to the meaty equation. The rest is, just kind of details.